Right, I think we are live right now. So let's start our session. So welcome everyone. Thank you very much for joining today, our special session for the PS Day. Before we start, myself, I'm Conrad Schmidt. I'm a PhD student here in Texas Tech University, and I'm gonna be moderating the session. And this event's a partnership between the IEEE PES Young Professionals Association and together with the IEEE PES Brain chapter from Texas Tech University. And besides like the usual sessions we usually see online, we are trying to bring something different. And today we have the virtual tour on GLEAMM, a real-scale microgrid facility. Our speaker here today is Dr. Manohar Shamana. And before we start, I'd like to introduce Dr. Shamana by having his bio here. So Dr. Manohar Shamana is a lecturer and a graduate advisor in the National Wind Institute at Texas Tech University, focused on clean energy integration in the electrical grid, education, and research. Before joining NEWI, he was with the Smart Grid Department of an electrical distribution utility, ComEd, and a renewable energy development and testing company, Group NAR. He also interned in the Power System Integration Group at the National Renewable Energy Laboratories. He received the master degree from Texas Tech University in 2011 and the PhD degree from the University of North Carolina at Charlotte in 2016, both in electrical engineering. He has several publications in leading power and energy-related venues. His research interests include modeling and analysis of active distribution networks for grid service and resilience benefits, cyber physical security, building energy management systems, and economic impacts of distributed energy resources. He currently serves as the principal investigator of the Texas Workforce Commission, Department of Energy, and Department of Defense grants. He's actively involved in the Global Laboratory of Energy Asset Management and Manufacture (GLEAMM) related activities to develop cyber-physical testbeds for research and education. The testbeds are being used for training critical infrastructure professionals and enrolled students. Thank you very much, Dr. Mana, for your time and being here today, sharing this amazing facility.
Thank you for the introduction, Conrad. Can you hear me, right? Can you
Yes,
start
I
it?
can hear you.
Thank you. So again, my name is Manohar Chamana. I'm an assistant professor here at Texas Tech University's Wind Energy program. In today's presentation, I'll be going over, introduction to the GLEAMM facility or the GLEAMM microgrid research facility that we have here, a real-world test bed that we can use, a megawatt scale test bed that we are currently using for research and education for our students here. So the outline for my presentation will be giving you an introduction to the GLEAMM microgrid. I'll be going over a DoD project that I'm a co-principal investigator of, and then we'll have a virtual tour of the actual facility that will be, being presented remotely by one of our students. So I'll be just going over the different resources that we have at the GLEAMM microgrid. So the purpose of a GLEAMM microgrid, which is in fact a very unique facility that not a lot of universities will have. You'll have a lot of national labs having real-world facilities for R&D, but at a university scale, we have a real-world microgrid of megawatt scale that is used primarily being used for commercializing new generation technologies and enhancing existing electricity grid towards smart, secure, and resilient energy systems. So we have a real-world test bed that we'll be looking at, in a few minutes, and then I'll be going over some different projects that we're working on, and the facility is being used for testing, demonstration from external institutions as well, and this is also being used to develop research and practical skills for our students to enhance their skills. The GLEAMM microgrid is located at Reese Technology Center, which is right here, which is about 6 or 7 miles from the actual campus. Our actual campus is main campus is at the center of Lubbock, Texas. Lubbock is in the West Texas region here in Texas. GLEAMM is located here and is on a former Air Force base. So we took the land from an Air Force base, retired Air Force base, and developed a megawatt scale microgrid that is currently being used for R&D. So this just shows you again a map of where we are located. So we'll be going over different resources at GLEAMM. We have the GLEAMM control center here, a 1 megawatt battery, and then an ESS battery, and then a solar plant of 150 kilowatts. So this is all TTU resources. Besides this, we have at the same location 3 wind turbines that are being operated by Sandia National Labs. That's a national lab in the US. And in fact, the Texas Tech's GLEAMM microgrid facility is electrically also connected through to these 3 turbines. So this is a very unique facility with 3 turbines connected to solar panel and a megawatt scale battery for research and development. So this is inside our control center. We'll be going over a virtual tour in a few minutes, but here is the main circuit panels. Here we have different resources inside the control facility itself. We have a battery here, and then some HMI systems that can be used for visualization. And besides that, we have a data center as well here that can be considered to be a critical load. And these are all our relays and control units that are connected to the microgrid to manage the facility specifically. So the GLEAMM microgrid consists of generation. We have a 1 MVA service power transformer. So we are connected to a South Plains Electric Co-op, which is a rural electric co-op, a distribution utility, and there is with so this is a microgrid. So the microgrid can be disconnected from the main grid by switching over to a diesel generator. The diesel generator is rated at 569 kVA. So while the generator, either in grid tied mode and islanded mode, you have the solar plant which can operate. It's rated at 150 kilowatts. So depending upon the current irradiance, it can also be online all the time, both in grid tied mode as well as in islanded mode. So besides that, we have 300 kVA turbines, which are not owned by Texas Tech, but it's operated by Sandia National Lab. But it is tied to our facility. So in fact, we can work with them to do any R&D tests, experiments, or for any education purpose as well. So besides that, we have a 1.6 kilo ampere hour lead acid battery. So this is a small scale battery which could be considered to be similar to a UPS for a critical load, which in this case is the data center load. And besides that, we have a 36 kVA EV emulator which can act like a load if it is charging, and can also act like a generator if it is discharging. So we can also test a vehicle to grid operation as well at this facility. Besides that, we have large scale loads, 500 kilowatt dynamic resistive load banks, 187.5 kilovolt ampere reactance dynamic inductive load bank. So essentially, we can emulate kilowatt and active and reactive power loads in this facility, and they can be scheduled as well as we go along. So besides that, we are considering 16.5 kV as a high performance computing load that is essentially being managed by a different research team here. But their main purpose is to ensure that no matter what, this critical load is always being served either by the grid or by the UPS, which is in this case the 1.6 kilo ampere lead acid battery if there was an outage. Besides that, we have small scale building loads, which is essentially the HVAC, lights, your server loads, and all this could be considered as internal building loads. So this are all the different elements you'll find the GLEAMM microgrid. Looking at the facilities topology here, on the left side, you see the electric diagram of the microgrid. So we are connected to the South Plains Electric Co-op utility. If you look at this, you have a transformer that steps down from 12.47 kV to about 480 volts. So the microgrid itself is being operated at 480 volts, and you have the EV emulator here, the different loads. You have the three wind turbines from Sandia, 150 kilowatt solar plant, and then you have the load banks, and then you have the critical load, which is the server that we have, and the UPS to ensure, as a backup, you have that battery for in case there was an outage. So you have the outback battery that is serving the critical load, and that is connected to the microgrid facility as well. So here are all our different resources which we'll be looking at live in a few minutes. So you have the grid here, the battery, load bank, server, diesel generator, solar plant, and then inside the facility you have this main circuit control system, and then the ATS, which is the automatic transfer switch, which will switch your grid to the island mode or the diesel generator in that case. And you have the HA panel and the outback, which is the battery that is this is the outback inverter we have here, which is used to regulate the battery in case there was an outage in the grid. So besides that, we have additional resources from Sandia. The 300 kilowatt, there are three of them, 300 kilowatts. So you get to about 900 kilowatts of wind generation max capacity that can be tied to this microgrid facilities. And besides that, you have the EV emulator, which is the vehicle to grid emulation in case you want to test out electric vehicle charging and discharging for different operations. All right, so for the control systems, we have an SCL 3530 real-time automation controller, and we have other control devices, hardware, such as the Raspberry Pis, microcontrollers, and PLCs to control the facility resources. For monitoring, we have eGauge, which will be able to monitor, the kilowatt consumption, reactive power, and all that can be measured and be stored in a database. We have a database that has the storage of all the real-time data from PV panels, the loads, and any other resources that we have at the GLEAMM facility. And then we have a simulator as well. If you're familiar with a real-time simulator, we have an OpenRT system as well, which can model your electric grid, anything that you want to model as far as the electric system goes, as well as you can. We have the capability to also model a network layer as well on top of the physical layer, and that will help us to do cybersecurity and any other control systems operations as well. That's what the simulation for simulation purpose. We have the OpenRT system that gives us that capability. So for the communication at the microgrid facility, this just shows you the communication systems for the different operations. So you have the human-machine interface that connects to the real-time automation controller. And then all the data that is being captured from the facility can be stored on the database. And we have the microgrid LAN here. So that's separate from our Texas Tech LAN to ensure that you have the capability to manage all the resources and at the same time be kind of disconnected from the TTU internet as well. So we have a local area network here with which manages the different in order to manage the networking of different devices here at the facility. Excuse me. So for the software, we have the SCL RTAC, which is able to communicate. So RTAC is able to communicate through different protocols like Modbus, DNP3, IEC 61850, and essentially for visualization of the operations, you have the human-machine interface built into the RTAC as well. So OpenRT and HyperSim are again used for real-time modeling and simulation. So we have the capability as well. Besides that, there is a software called Exata CPS, which is a network layer simulator where you can simulate or model different communication devices like routers, switches, your control devices or monitoring devices can all be emulated on the network layer for understanding the cyber physical operations, and also have the ability to create a cyber attack and look at the effects on the physical layer side as well. So besides that, we have other software like Power World, which is for offline modeling, Voltron, which enables us to do advanced energy management system algorithms and management of the resources as well. So again, Voltron is a platform that is currently being used for a project. Essentially, it has many functionalities such as it can connect to your Python agents. It can connect to real world devices as well externally, and essentially it works on a Raspberry Pi. And then we have for optimization the GAMS platform, which can be tied to Voltron to manage the resources. If you need to optimize the power in energy systems, we have GAMS, which is connected to Voltron. And then through Voltron, you manage the actual microgrid resources. So we have Homer Pro that is primarily being used for analyzing the techno-economic benefits of the microgrid or any other system that we have. So as far as the human machine interface goes, we have a HMI here at the GLEAMM, which helps us to visualize the operations of the microgrid. And again, you can look at the power being produced at the current instant and what are the current devices that are connected. So this just shows you the HMI. So all the red blocks that you see are the connected devices, and the green ones are disconnected. So red ones means it's connected. And besides that, you can also look at the HMI for the critical facility, which is the data center, and you have the backup battery here, and you can actually look at what is the energy being required by the data center and what is the energy being supplied from the grid or the battery in this case. And this is the RTEC that we have here. So for the historian, which is essentially storing all the microgrid measurements, we have the Dell server here, which will collect all the data for future analysis. You can do big data analysis in the future for machine learning as well. So we need to collect all the real world data for our analysis. That is being done here. So for the microgrid model, we can model this on RT-Lab or HyperSim. So we have the actual microgrid also modeled on both RT-Lab and HyperSim, which runs on the OpenRT. So with this, we'll be able to add any additional resources or implement any control algorithms and actually look at how it works on the real-time simulation environment before you actually implement it on the real microgrid. So we have the capabilities as well here at the GLEAMM facility. And I just wanted to quickly go over the energy management system here. This is an example of what was collected in the past for a microgrid operation. So the green curve that you see here is the power being generated by the PV. So as you can see here, about 7:30 a.m. you have the PV being the 150 kilowatt PV starts producing our power, and then as the time goes on, you see the power increasing, and in the afternoon you have the peak, and then it goes down. So during this time, we just wanted to test out the charging of the small scale battery that we have from Outback. So we just show you here the power of the charging of the battery during from 8 a.m. to about 11 a.m. So we have different graphs here that show the power outputs, battery commands for charging and discharging, the voltage level of the battery, and then this is just an operation of charging and discharging that could happen. And during that time, we also want to make sure that either when you have the grid available or the battery, so that the load is always remaining constant. So that is shown here by this green line. So the green line shows the power being consumed by the load, and at different times of the day, you can have power being served by just the grid or a combination of the grid and the battery as well to serve the load. We just wanted to test that out in this operation. So this just shows you a simple use case for managing the critical load using the Outback battery as well as the grid. So I'll now move over to a DoD project. This is being led by me and Dr. Stephen Bay here. So this is a project with the Department of Defense, Internet of Network Microgrid Solution for Scalable Agile Microgrids. So what we wanted to do here was talk about the critical facilities resiliency, microgrids management, smart building demand response, DRS optimization, and then carbon footprint reduction. So these are all what the Department of Defense is interested in, and we wanted to test out the solutions here before we implement that at a DoD pace. Excuse me. So for this project, we are making use of the microgrid facility that we have here. This is the GLEAMM building here. We have one more building at Rees, and then we have the Group Nair building here, which is essentially one more facility that with whom we work. And this just shows you how we can remotely manage different resources that are located in the same area, right? So we have about the distance between the GLEAMM building and the Rees building is about 1.8 miles, and we have a remote connection between these two facilities, and as well as the Group Nair building. So we wanted to test out remote communication. So right now, Group Nair is a facility that has its own microgrid, and then you have GLEAMM building, which has which is operated by Texas Tech. So we just wanted to also show that we are able to remotely communicate between two microgrids. And we have that setup also done using remote connections. All right, so here's the GLEAMM building that I was mentioning up to now, and then you have the Group Nair building, and these are two different LANs. And in order to manage different resources, you can have a centralized control unit sitting at Group Nair's building and manage our DR resources. So we wanted to test that out, and we were able to successfully do that through VPN into the firewalls and manage the different resources that we have here at GLEAMM. And at Group Nair's building itself, we have some resources like Solar Edge, a battery, and an inverter as well. So the GLEAMM's microgrid has different capabilities that enable us to demonstrate physical capability, electric capability, hardware, software research, and then expansion as well. So primarily, again, I just wanted to stress here is that we have different resources to test different algorithms, to acquire data for future analysis, for machine learning and all that purpose, and as well as expand as well. If you needed to include a new resource into the facility, we have the capability as well at GLEAMM. So for our partnerships, these are again all our different partners with whom we work for both research as well as part of suppliers for our projects. So with this, we'll move on to the virtual tour, which will be in a few seconds right now.
All right, thank you very much, Dr. Shamana. It was a really interesting presentation and good background for the virtual tour right now. I would like to invite all the attendees. We are broadcasting different platforms, so feel free to drop any question that you have on the chat that you are watching our session, and we are going to receive all the questions here, and Dr. Shamana is going to address them in the end, okay? Thank you very much. And now we have the virtual tour, which Robin is going to be presenting the microgrid, and Dr. Shamana is going to be explaining each device.
All right, so thank you, Robin. So just wanted to again start with the actual live tour of our facility here. So what we currently look at is the south. If you remember, I mentioned that the grid is from the South Plains Electric Co-op. So this is the main transformer which steps down the 12.47 kV to 480 volts before it is run down to our electric control center. So we have the overhead lines from South Plains Electric Co-op, which serves the microgrid. And next, we see the backside of the PV panels So as we move along, we can next maybe look at yeah. So this is just the backside of the PV panels. If you remember, I had mentioned this is about 150 kilowatts of PV PV panels, uh, and right now we see the entrance of the facility. It's one of the backside entrance of the facility. To the left hand side, this is the 569 kV diesel generator that is essentially like a backup generator to the facility if the grid was lost. So this is from Caterpillar, and the source of power is the diesel furnace. And then we have the two resistive load banks rated at 500 kilowatts. So we have about 1000 kilowatt of capacity of resistive loads that we can control. So this again can be controlled through steps, right? So we need not be rated at 1000 kilowatts. You can get about 100 200 kilowatts through set points, and this is being managed through Modbus communications. And this is that 180 kilovolt ampere reactive load bank. So with this, we have a total combination of active and reactive power loads that can be controlled for studies of the microgrid. So this is an interesting one. This transformer that we see here is what is connecting the three wind turbines from Sandia, and Robin will in fact just show you also the turbine. Okay, so before you go, can you show this as well? So we have that 1 megawatt battery bank as well, which unfortunately is not functional. I should be let you know, but this has the capability to about produce about 1 megawatts of capacity and both charging and discharging. So this is rated at 1 megawatt. Okay. So to the far end, you can see the three turbines. One of the turbine, a couple of turbines do not have the blades, but in fact, if you decide to do battery, diesel generator, PV, and wind, we definitely can include that into our system for different purposes. And here's that 150 kilowatt PV panel that we see here. This is being served by 5 times 30 kilo watt inverters from SMA. Now we'll get into the actual microgrid control center or facility. So here, right at the entrance, this is the switchgear panels for the grid connection. So while the grid is being tied to the microgrid, we can actually so your video just stopped, Robin. All right. So let me again quickly get into this. So we have the main switch gear, which is to the grid, and then we have the automatic transfer switch. So the ATS is essentially which manages the switching between grid tied to islanded mode, which is connecting the grid to switching from grid tied to the diesel generator. And once you have a diesel generator, the diesel generator will be the primary source to the microgrid. And to the right, we have the panels for the operations within the microgrid facility to the loads, the HVAC, and all the other smaller resources that we have in the microgrid. Even the 150 kilowatt PV inverter is connected to this panel. So these are all the switch gears system for that. Again, this is just the safety purpose, for our facility. Okay, to the right hand, we have now we are just showing you the load banks. So we have a lighting load bank here that can also be used as a controllable load source for managing the load. If you need to show the operation of load controls, you can also do that through this uh, lighting load bank. And then we have this backup The UPS for the critical load, we have about 1.6 kilovolt ampere hour uh, battery bank, and then we have the outback inverters to manage the operations of the backup batteries. So this is one more lightning load bank that we have. These are all LEDs. The other one was tube lights, and this is for LED management of the lights. And then we have the EV emulator to the left hand side, which can do your EV emulation charging and discharging to the facilities. So we have these panels that are connected to the HVAC system as well as the EV emulator. And then this should be the critical load. So this is essentially like the data center being managed by one more research group, but this is considered to be a critical load. And no matter what, our main purpose is to ensure that this critical load is being served both in grid tied as well as in islanded mode. So we'll now get into the actual heart of the management of the microgrid facility. We have the real-time automation controller, or RTAC, which manages the controls of the different DERs, and you can actually look at the actual visualization of the load and PV and battery as well here in this on the screen. So on the TV, we have the HMI, or the human machine interface, on the left hand side of the microgrid, the GLEAMM microgrid facility, which shows the current resources that we have and actually gives us a better view of what is being operated and what is currently disconnected. If you see, all the red ones are being operated, and green are means the breaker is open. And to the right hand side, we have the data capture of the PV. If you look at the PV, it's on the green shaded region. And then you have the loads as well being shown as the red region. So this just shows you, about 24 hours of data captured, and actually display that on our screen here. So I think with this, we are done with the virtual tour of our facility, and I think we should be now open to questions and answers.
Fantastic. Thank you very much, Dr. Sharmana. It was really interesting to see, like, from the inside of the facility. I know it's like a kind of like a different session, so I hope everyone joined it here. And now we are open for any question. So if you are joining the session from different platforms, just feel free to drop your question in the chat that Dr. Sharmana is going to be addressing here. While we just wait for the questions, I'd like to invite Dr. Sharmana if you can talk a little bit more about the partnership that GLEAMM has with the Sandia and the wind turbines. GLEAMM is involved with several industry and companies. So if you can speak a little bit more about that.
Yeah, definitely. So primarily, the Sandia turbines are being used for multiple reasons. They have been used in the past for testing wake effects for testing out different control operations. And now that there is Sandia turbines, which is located at the same former Air Force base as GLEAMM, there was agreement between Sandia, which is a national laboratory, and Texas Tech, which is a university, has its own uh, microgrid facility to work on research grants as we go along. Our purpose is to work together to go after funding to actually test new operations of microgrids that will have a co-located PV, battery, and wind, right? So a lot of locations usually just have PV and batteries, right? So, but in this case, this is a very unique facility that has a PV, wind, and battery. And uh, primarily, what see here is that, I mean, if you kind of can think about it, right? So PV is not available during the nighttime, but you have the wind. So PV with wind, and then you have battery, right? So these three together working, you can actually develop new test cases to manage all this three different types of resources, and actually look at what amount of load can be served just by renewable energy sources and battery, right? So that way you can kind of do studies on off-grid off-grid systems that have just renewable sources with a battery system, as well as off-grid plants that might have co-located PV, battery, and wind. So those are something that we're planning to do in the future as part of our R&D goals.
That's fantastic. And I believe like most people like watching us right now, they might be interested about how how they can get in touch with GLEAMM, or like how they can start a partnership for like students, research, or even like companies. So how would you suggest like to start this communication and potentially a partnership?
Yeah, so for students, I would say that we are always open to hire students depending on the funding availability. But as you can see here, every for as far as students goes, our research facility is being managed by our students. They work on research projects, develop new algorithms, test them out. So for their master thesis or PhD, for the dissertation, they can use this facility as a test bed to for their dissertation purpose. And at the same time, when we work with national laboratories or any of the private partners, we have the ability to work with them as well, where they can come down here, implement their algorithms on our facility, work together on a DOE project or a DoD grant. And I see that, okay, potentially we can test out new solutions here within our facility that can be commercialized as well. So, at GLEAMM, the primary purpose is to test out new algorithms and as well as commercialize new products into the market as well. That's how I see, the future of GLEAMM.
It's perfect. Thank you very much.
No
Let's
problem.
see. Still don't have any question in the chat. Let's wait a few minutes. And in any case, they can contact you, Dr. Sherman, right?
Yeah, definitely. I think we are open to partner on research grants as well as students who are interested to join our lab. As research assistants, graduate assistants. Please feel free to contact me if you're interested to do that.
Right. Sounds good. Okay. I think that's the our session for today. Before closing, I would like to thank Dr. Shamana for your time and to be here and share with us this amazing facility and all the capabilities inside. So thank you very much for being here with us.
No problem, pleasure. Thank you.
I also would like to thank for the IEEE PES YP for like initializing this idea, and also the IEEE PES Brain chapter from Texas Tech University, which are together like they are doing this event for the IEEE PES Day Celebration of 2022. And I hope you all have a good day ahead or evening, depending where you are. So thank you very much. Really appreciate all your presence here, and I hope this session was interesting for you as well.